The purpose of this lesson is to determine the centroid point or the center of mass for a uniform plate. Okay, let's start with a system of particles. We have on a plane. Okay, so we have a xy plane, and then we have particles in this assembly or in this system. We have one, two, three, four. So this is four particles, and each particles is represented by coordinate x, n. So any particle represented by this coordinate, and each of them they have the same mass. Okay, so here m n. Okay, for example, this is x1 y1, this is x2 y2, and it has a mass of m2, it has a mass of m1. Okay, so arbitrary points is presented by n. Okay, so in this system, in this system consisting of several particles, they have a center of mass. That means the center of mass is the balancing point of an assembly. So this means, for example, we have this distribution. So the center of this distribution is located here, for example. So this G is what we call the center of mass of this system, which is denoted by X bar and Y bar. That means this is the center of X and Y axis of the system. Okay, so let us recall back about torque. Torque is the product of force. So in this case, if we have a particle which is located, for example, there is um, a, a road, and this is a mass. Okay, and this is the axis of rotation. So the torque is the product of the weight and the distance of the mass from the point of action. So the torque indicates how easy a system can be rotated. If if the weight is so high, it can easily rotate, and also if it is farther than the action of the point of action, it becomes easier to rotate. Okay, yeah, so that's why if we have a door, this is door, and this is knob. So the knob should be away than the rotation point, so that it is easier for the system to rotate. Okay, so consider in this system, there is no gravity, so that means we don't have this G. Okay. But we can introduce another property, which is we call a moment. So moment is just the product of the mass and the distance without considering the gravity. So we can say this is a weightless system. Okay, so the moment is just the multiplication of m and the distance from the center of the system. So this is the R is the system, the distance from the system. From the system. Okay, so that's we will so if the system is in the balance, mechanically balanced, the total moment of each of the particle must be zero. Okay, so that will become equilibrium for the system, the mechanical equilibrium. Okay, so in that case, we have to calculate the moment for each of the particle. So the moment is the mass times the distance from the center of the mass, or center of the mass, or center of the system. So the distance is Sn minus x. This is what this we consider first for the x-axis first. So this is just the distance from this to this is here, Sn minus x, times the mass of the particle. So that is the moment for one particle. But since we have many particles, which is we have n particle, so we have to add them up, sum them up for each moment where the point of the center of mass here, the sum of those moments must be equal to 0. So that the point of the center of mass represent the center of the this assembly or this distribution. Okay, so if you look into this properly, you can expand this bracket so you have that you can have mn times xn and also mn times x bar, which is this is the average of the distance or the point of the center of the distribution. Okay, so you equate to equal to 0, then we can expand. You can expand so that they have different separate terms. Okay, so so that this is negative, you can put this on the right side. So this is what we've done. What we have done here, so this is on the right side. So this term equal to this term, and then remember that x this x bar is constant. This is located here, so it is not related to any n. So we can put it out. So we can put it out here. Okay, so this is, you can see this is the sum. This is the individual mass, but when you sum them up, that means this indicate the total mass of the system. Okay, the total mass of the system. So you have you can represent it as one mass, the total mass. All right. So when you present it as a total mass, okay, m, then you can bring them to the left, but bottom. So when we arrange back, we have this 1 over total mass, the summation of all the particles, the product of the mass and the distance, and the coordinate. Okay, so that means the center of mass for this system, for x-axis, we can calculate by using this relation, and in the similar way, we can calculate we can determine the point for y. So here we have shown that how we can get the position of the center of mass of a system of many particles. All right. So if we have so many particles, okay, for example, in a plate. Now we have a plate. Okay, in this plate, we can consider this very thin plate, and there are so many particles, uncounted. Okay, so it is not possible to calculate one by one because this, so n is so many. Okay, so in this case, we want to calculate the center of mass of this particle of this plate. So the center of mass, we can approximate the point of the balancing, the point of balance. So if we put our hand there, so it will be balanced. So this is not because this is very soft piece of paper. So, but if you have a plate, the center of point should balance if the gravity exists. Should balance the plate. Okay, so now we want to determine the position of the center of mass for the uniform plate. So uniform plate means that every point it has a shape. So for example, if you put this square and you put this square, so the same square will have the same mass. That is what we call uniform plate. That means the mass is equally distributed all around the area. That is what we call uniform plane. So when we want to proceed, we have to get one information about the plate. So what is it here? The information that we should get from the plate is mass per unit area. Okay, mass per unit area or kilogram per meter square. Okay, so so this is same, both are the same. But first, let's consider the x-axis. How we can get the center of mass along x-axis. Right, so we have mu equal to ma, then we just rearrange back m equal to mu a because we want to use it again. Okay, so suppose that we take a strip of an area delta A. So the area is the height multiplied by the width, right? So the height is Vx. This is a function which represented the height of the strip. Multiplied by delta x, we get the area of the delta A. So delta A is approximately, because it is not perfect square, right? So that's why we use this approximately equal to the distance, this length, the x is the length, multiplied by the width. So we have this relation. Okay, so this strip, if we cut it and we weigh it, so it should have a mass. So the mass of this strip is delta m. Okay, the mass of this strip is delta m, which is approximately equal to mu times delta A, right, from here, because mu is fixed. Mu is a fixed number, it's a constant, it is a ratio, but m depends on A. So if we have large area, we have a large mass. Okay, so that's why we use this relation, delta m is approximately equal to mu times delta A. And then delta E is from above, right? So we can include into this relation. Okay, again, we have to use the moment relation. So moment is the multiplication of mass and distance. Okay, from here, right? Moments and distance. Okay, for the x-axis, so distance times mass or mass times distance is just the same. Okay, so and this is equal to x minus s, the x bar. Okay, dm, you can take it from here. So we can substitute. Over there. Now we have all information ready for us to calculate the total moment from here to here. We want to swipe from A to B. So here. Okay. So this is for one strip. This is for one strip, but we want to have all the strip. So that means we just write down all of the strip available. That means this is x. Sorry, so here. So we can expand this bracket x times mu v dx. So we have here, and then minus, because minus x u v x delta x. Okay, and this should be equal to 0. Similar like this. Okay, Okay, the moment of all the strips, the total moment of the strip must be equal to 0. So we have to set them as an equilibrium condition. Okay, then you see this is negative. We can put it on the right side. So that's why we have an equivalence here. And then also this x and mu can be put outside because it is just constant. This is also can be put outside. So that's why we have this is outside, this is outside. Okay, and then we cut it out because left and right. Okay, and then you look into this relation. Okay, this relation is equal to area, total area. Actually, total area, because this street, we have many streets. V times delta A, and then you swipe from A to B. You swipe it, so you have a total area actually. So you have XA. So this is just the area. Okay, and then this one, this is the integration. Okay, so you can put it here. X, this is A, so you can rearrange back, you get this. Then finally, this can be notated in the integration form. So 1 over area from A to B, and this is V, this length, the X. Okay, so this is how we can calculate the center of mass, or we call it centroid for your uniform plane, the centroid point for x-axis. Similarly, for y-axis, you can just change the orientation. So delta A here, the street here, is the multiplication of the distance hy times delta y, you get the area. Then similarly, for the mass, it is the multiplication of the mass per unit area times the area. So you can use this and follow, then you can get the similar relation for y. Okay, so that was the story about center of mass or centroid for the uniform plane.